Welcome to the demo session of Bautik Academy of Physics. For the next few minutes, we are going to see a very important technique from mathematical physics. Actually, this is a very useful technique as well, and it's been widely using in different branches of science, such as chemistry, physics, computer science, biology, in fact, literally everywhere. Yes, you might have guessed it by now. It's called Fourier series. You might have done a lot of calculations or problems using the Fourier series. You might have seen some mathematical expressions of Fourier series. So you might wonder, like, what's a big deal with Fourier series? We know already this, right? But today we are going to present Fourier series in a bit different way. Meaning we're going to look at this technique from a different perspective, a visual perspective, so that you will never forget what a Fourier series is. Okay, to begin with, let me draw a Cartesian coordinate system with axes x and y. Now I'm going to set a point somewhere here and I'm going to call it P. And this point P can be completely defined with a pair of numerical numbers. Let me call it x1 and y1. Okay, what is x1? x1 is the x component of the point P. So this is my x1 and this is my y1. Okay, so now the same point P can be completely defined in terms of another pair of numbers. So in order to know that, I just drew a line from the origin to the point P, and I represented this line length as r1, and the theta, or the angle between the line to the x-axis, is theta 1. Okay, let me call it as theta 1. Okay, so the P point can now be expressed in terms of r1 and theta 1. We can simply write it as x1 is equal to r1 cos theta 1 and y1 is equal to r1 sin theta 1. Okay, so let me call this as equation 1. Okay, now for my personal convenience, I'm going to represent it r1 as c1. Okay, no big deal. This is just a simple substitution. And according to that, the equations will be x1 is equal to c1 cos theta 1 and y1 is equal to c2 cos theta 2. Okay, you can call it as equation number 2 if you want. Okay, the next big thing is I am going to change this Cartesian coordinate systems. The same figure over here. And now what I'm going to do is, instead of y, I'm going to replace it with iy, where I is root of -1. Okay, so I is the complex number which has a numerical value root of -1. You know, it has a very beautiful geometrical meaning which you will see in the regular classes in Bautik. Okay, we'll see all that in later classes. For now, yes, I is just a complex number. So when I replace y with iy, I should make a change over here. Instead of y, I have iy, and instead of y1, I'm going to have iy1. So instead of y1 over here, okay, the same thing is applied. Okay, now if I write the same conversion equations as in equation number 2, I can write x1 is equal to c1 cos theta 1. There is no change in the equation number in the first equation, and iy1 is equal to ic1 sin theta 1. In terms of x1 and iy1, the question is how to represent this point P. Okay, now I am going to represent the same point P in terms of x1 and iy1. So in terms of x1 and iy1, the point P will be x1 plus iy1. Okay, before we had x1 comma y1, it was just a set of numbers, or r1 comma theta 1. Right now we have a plus sign. This is equivalent to, or similar to the vector addition. For example, if this is your x1 and if this is your iy1, like two components of a vector, so when you add these two vectors, that is vector iy1 and vector x1, you get another vector corresponding to this new green line. Okay, and the tip of this vector can be described as x1 plus iy1. What I did was I just converted the Cartesian coordinate systems into a complex plane. So the point P, if I rewrite it over here, point P is now represented in terms of x1 plus iy1. Over here you can write it as c1 cos theta 1 plus I c1 sin theta 1. Okay, let me call this equation as equation number 4. Okay, now let me introduce a new formula. We call it Euler's formula. And this formula says that c1 cos theta 1 plus I c1 sin theta 1 is equal to c1 e raised to I. We have been considering a point on the complex plane which was fixed. That is, the point was this point P, which is represented using c1 e raised to I theta 1. It's a complex number, which is I and Iy, of course. I was saying it is fixed. It's because c1 is not a function of time, or it is not a function of anything, and theta 1 is also not a function of time. Okay, since this is not changing, since the point P is a constant on the complex plane, this will remain on the complex plane forever. Okay, and there is not much exciting thing about a fixed point. So what I'm going to do is I'm going to assign a time function to our angle theta. That is, I'm going to say that theta is nothing but a function of t, and I'm going to assign a function explicitly over here, which is omega 0 t. So what does that mean? That means as time increases, the angle theta increases. Meaning, if this is your point, some time t is equal to 0, as time progresses, this point is going to move from here, somewhere here or here or here, right? It will start to move, basically. Now I'm going to impose another restriction, that the point c1, which is the length of the point, it is not a function of t. It is going to be a constant, meaning that the length, which is this line, is not going to change. Okay, so the motion of this point is restricted now, and we will see how the point is going to move according to these two conditions. Okay, let me call these conditions as conditions 1. So according to conditions 1, let's see how this point is going to move on the complex plane. So you have the complex plane I and Iy. So you have the point P, and this is my angle theta of t, which is equal to omega 0 t. Okay, so I have explicitly defined a function. So you might ask me, is there any problem if I define my function theta of t as, let's say, some 5t square, or let's say some 3 root t? Actually, in principle, there is no problem in defining the theta function with any function that you want. But the reason why I defined theta of t as omega 0 t, it's because we have a certain aim, because we are trying to derive an expression for Fourier series. And because of that, I restricted my function as a linear function of time t. Okay, now coming back to the main problem, like we want to know how this point is going to move. So we know that the length c1 is not going to change, but the angle, which is theta of t, is going to change. So if t is equal to 1, my theta of t is equal to omega 0, which is what I have written over here. Okay, this is my initial time. Now when t equal to 2, theta of t is equal to 2 times omega naught, and when t equal to 3, theta of t is going to be 3 times omega naught. So this means, let's say if this is my initial angle omega naught at time t equal to 1. So let me clear all this first. Okay, so this is my omega naught at time t equal to 1. Now what happens at some later time t equal to 2? The angle became 2 times omega naught. That means now the angle is 2 times of initial angle. So let's say that corresponds to a point somewhere here. So P is now here. Okay, so maybe I will use a different color. So this, according to this, this is the angle. That angle is 2 times omega naught. Okay, now the P has changed from this point to this point. Okay, now what happens when t equal to 3? What is the angle? 3 times of omega naught. Meaning, okay, let me take this over here. So if I represent the point, another point over here, that corresponds to the angle 3 times omega naught. Meaning, again, the point P has displaced from this point to another point. Okay, this is my new point P. Okay, now if you continue doing this, you will get exactly a circle with radius r, or c1 actually, sorry for that. You'll get a circle with radius c1. That's what you're going to get. This means as the time progresses, this point P will start to move, and finally reach at its initial point, and again it will continue because we are not restricting time. So this is basically, we can call it as a spinning vector. So this line is going to spin about the origin forever and ever. Okay, so this is called a spinning vector. So if you represent this spinning vector in terms of our initial c1 e raised to I theta 1, let me write it, how to represent a spinning vector. So I'll write it over here. This is very simple because what you all need to do is to substitute the time function instead of theta 1. So c1 e raised to I omega 0 t. As you already know, omega naught can also be represented as 2 pi nu naught, where nu naught is the frequency of the spinning vector. Now we have seen that this point rotates and forms a circle. And we have also seen that this rotates anti-clockwise. Why it is anti-clockwise? Because theta is increasing, this part is increasing, and because of that, we know with convention the theta starts from here. If this is my axis x and iy, if this is my length, if this is my some length or some vector with theta is equal to 0, as theta increases, the vector increases this way. Okay, so basically it is rotating anti-clockwise. So when theta increases, the corresponding vector rotates anti-clockwise. So this is anti-clockwise. If this is anti-clockwise, how do you represent a point that is rotating clockwise? It is very simple. Just put a negative over the argument. E raised to minus I 2 pi mu naught t. Now this is very clear because as the magnitude of the theta increases, it is increasing in the negative direction. That is, this time the vector is rotating anti-clockwise. Okay, this is the direction of the negative angle. Okay, now we have represented a spinning vector or a spinning point, these two, in anti-clockwise as well as in clockwise directions. So this is clockwise, as we have already discussed. Now let me finalize this. What we have already seen is a single vector that can either spin anti-clockwise or clockwise. So what if I introduce another vector? So this is my first vector P. Let's say if I introduce another vector, some P prime. This time its length is C2, this length was C1, and angle was, theta. Okay, let me write it this way. Angle was omega 0 t. Okay, so in this case, I have introduced another vector with an angle 2 times omega 0 t. Okay, this is where the change happens. So what did I do? I introduced another vector P prime, this time with a different scale or a different length C2 and a different angle which is 2 times the angle of my previous vector or my previous point. Okay, so how do I represent this point P1? P1 can be represented as C2 e raised to I 2 pi 2 times mu naught t. Okay, and depending on whether it is anti-clockwise or clockwise, you can have plus or minus. So this is how I represent P prime. Now if I add another vector, let's say P double prime, I can have another complex notation corresponding to that. So I'm going to say C3 e raised to plus or minus I 2 pi. This time, let's say the angle is 3 times mu naught of t. Okay, so the only change that I'm doing is, as I add number of vectors, I add a number here. That is, if the frequency of my first vector is mu naught, the frequency of my second vector is 2 mu naught, the frequency of my third vector is 3 mu naught. So if I add n vectors, the frequency of my nth vector is n times mu naught. So depending on whether it is anti-clockwise or clockwise, this will take symbols. If it is plus, it is anti-clockwise. If it is minus, it is clockwise. Okay, so what I just did was I built or I constructed a lot of vectors on a complex plane with different frequencies. Those are rotating either clockwise or anti-clockwise. Okay, so if you consider this particular vector, that is the nth vector with a spinning frequency n times mu naught. So how do you represent that point? Let's say my p-nth point. Okay, this is again plus or minus. So this is how you represent the nth point. Now what I'm going to do is to add all these vectors. Okay, I have now n vectors. I'm going to add all these vectors. Some vectors are spinning clockwise. Some vectors are spinning anti-clockwise. I'm going to add all this. How do I represent that addition formula? So you can use a sigma notation that you are already familiar with. So I'm going to use that. So sigma Cn e raised to I 2 pi n mu naught times t. So this is what I get if I add all these vectors, all spinning vectors, results in this. Okay, now I'm going to say that n runs from negative infinity. That is, let's say I built or I construct infinite vectors. Okay, which is not practically possible, but theoretically you can always write that. So n runs from negative infinity to positive infinity. So I just constructed a summation formula, and its physical meaning is nothing but adding infinite spinning vectors and each vector has a frequency which is an integer multiple. Okay, so because as you have already seen, n can take plus or minus 1, plus or minus 2, plus or minus 3 in general. Now let's define Fourier series. Okay, so what we have written over here, that is a summation of spinning vectors, can be used to represent many functions, not any functions, but many functions. So I'm going to rewrite this function or represent this function as f of t. So this means if you have a function f of t that satisfies a certain set of conditions, we will see that conditions not today but sometime later. So let's say if the function satisfies a certain set of conditions, you can always represent this function as a summation of spinning vectors. Okay, and this is called Fourier series, and I would say that this is the most useful formula of Fourier series. If you know this formula, now you know how to derive this formula, you know the physical concept behind this formula, and if you know this formula, you can derive all other different expressions of Fourier series of a function. Okay, so this Fourier series was invented by Joseph Fourier in 1807, if I'm right, and he invented this Fourier technique in order to solve his heat diffusion equation in metal rods. Okay, now the fun part begins. Now let's see Fourier series in action. Okay, here you can see two plots, one on the left side and one on the right side. So on the left side, you can see three different circles. These three different circles correspond to the path of three different moving points. On the right side, correspondingly, we are going to plot the y component at any instant. So let's see how this works. Now you can see that when it starts to move, it is forming three different sine waves on the right plot. Now let's add these three different rotating points, just like the summation that we have written before. Now when you add these three rotating waves, we are going to get the corresponding resultant y component. Let's see how it looks like. As you can see over here, it's slowly forming a square pulse. Just like this square periodic function, in principle you can build any periodic functions possible. Maybe you need more number of rotating waves with different theta values as well as different magnitudes. That's what you all have to find it out in order to construct a function that you can think of. I hope you have enjoyed this demonstration a lot. Join us and we'll have more fun like this.